Today we learn about the relations. Before we start the relations, let me recall the Cartesian product of sets. What do you mean by Cartesian product of sets? Suppose A and B are any two non-empty sets, then the Cartesian product of these two sets is set of all ordered pairs in which the first element belongs to the first set and second element belongs to the second set. That is, suppose set A, set B, which is having the elements 1, 2, 3, 4. Then A cross B is written as set of all ordered pairs such that the first set of all possible ordered pairs such that first element belongs to the first set, second element belongs to the second set only. That is 1, 3, 1, 4, 2, 3, 2, 4. That is, Cartesian product of two sets is set of all ordered pairs in which first element belongs to the first set, second element compulsorily it must belongs to the second set only. Now, the same way we can define the Cartesian product on a single set also. That is, X, it is having the elements 1, 2, 1, 2. That is, Cartesian product X cross X is equals to, so how do you write this? Set of all ordered pairs 1, 1, 1, 2, 2, 1, 2, 2. So this is about the Cartesian product of two sets. In the similar manner, we can have Cartesian product of three sets also. That is, Cartesian product of three sets is nothing but set of all ordered triplet, whereas in Cartesian product we are having all ordered pairs, whereas here ordered triplets in which first element belongs to the first set, second element belongs to the second set, and third element belong to the third set. This is about the Cartesian product of two sets as well as three sets. Now, if A is having two elements, B is having three elements, then Cartesian product A cross B will be having n of A into n of B. That is 2 into 3, that is equals to 6 elements. So once again, if A is having two elements, B is having three elements, then its Cartesian product will be having 2 into 3, 6 elements or 6 ordered pairs. Now, let me talk about the subsets. So, suppose A is equals to 1, 2, 3. Then, number of subsets will be equals to 2 to the power of n of A is nothing but 2 cube is equals to 8. Suppose A cross B or A cross A, whatever it may be, A cross A will be having, what are the elements? 1, 1 and so on up to 3, 3. So n of A cross A is equals to 3 into 3, that is equal to 9. So number of subsets of A cross A is equal to 2 to the power of n of A cross A, that is nothing but 2 to the power of 9. So once again I repeat, if A is having 3 elements, then the number of subsets of A is equals to 2 to the power of n of A is equals to 8 elements, 8 subsets. Then if A cross A is having 9 elements, then number of subsets of A cross A is equals to 2 to the power of 9. Next, relation. What do you mean by relation? Relation is subset of the Cartesian product. So relation is just subset of the Cartesian product of two sets. Now, how many relations are possible? Once again, relation is nothing but subset of the Cartesian product x and y. Now, how many relations are possible is nothing but number of subsets of x cross y, because relation is nothing but subset of x cross y. Therefore, number of relations is nothing but number of subsets of x cross y. Now, if A is having P elements and B is having Q elements, then n of A cross B, that means A cross B will be having P into Q elements. Therefore, number of relations possible is nothing but number of subsets of x cross y is nothing but 2 to the power of P into Q. So example, if n of A is having 2 elements, n of B will be having 3 elements, then n of A cross B is equals to 2 into 3, that is equals to 6 elements. Now, how many relations are possible here? So relation is nothing but subset of x cross y. So therefore number of relations from A to B is nothing but number of subsets of A cross B is nothing but 2 to the power of 6. Is it clear? Next, come to the types of relation. Now, in this, first one is empty relation or void relation or null relation. What do you mean by empty relation? A relation in which no element is present is called empty relation. Now, how do you denote empty relation? Empty relation is denoted by null set. Suppose, let me consider a relation on a set X is called an empty relation if no element of X is related to any element of X. Now, let me consider one example. X is equal to 1, 2, and X cross X is equal to 1, 1, 1, 2, 2, 1, 2, 2. So this is X cross X. Relation is defined on X means, so relation is subset of X cross X. So X cross X we have taken. Now relation I am defining as set of all ordered pairs. Relation, how do you write relation? Relation is nothing but subset of Cartesian product. Cartesian product is nothing but set of all ordered pairs. So relation is also consisting ordered pairs only. Ordered pairs such that A plus B is equal to 5. Now you see, when you add any of these two, it will never be equal to 5. Therefore, this relation, no element is existing. So it is nothing but null relation. Next, come to universal relation. What is universal relation? Universal relation is a relation such that which is equivalent to Cartesian product of the sets. Now let we consider the same example. X is equal to 1, 2. X cross X is equal to 1, 1, 1, 2, 2, 1, 2, 2. Now relation is defined as set of all ordered pairs such that A plus B is less than 5 is nothing but when sum is less than 5 means it comes as same thing is nothing but X cross X. Therefore the relation itself is a Cartesian product, so we call it as a universal relation. Now let me repeat once again. Empty relation. A relation on X is said to be empty relation if there does not exist any element or any ordered pair. Universal relation is a relation which is equivalent to its Cartesian product. Next, come to identity relation and reflexive relation. What are the differences between identity relation and reflexive relation? So once we come to know identity relation, what is identity relation, what is reflexive relation, then what are the differences between them, let me say it. Identity relation. Let A be any set. Suppose we take A is equal to 1, 2, 3. Then identity relation, once again I'm repeating, relation is subset of the Cartesian product. Now R is defined on A means R is subset of A cross A. So A cross A consists of ordered pairs, so relation is also consisting of ordered pairs only. Now we have taken a set A is equals to 1, 2, 3. Now I am defining the relation on A as every element is related to itself only. Every element is related to itself only. So that means 1, 1 is related to 1, 2, 2 is related to 2, 3 is related to 3 only. So if every element is related to itself, then such relations are called as identity relations. So once again, identity relation means every element must be related to itself and only those elements must be present in the relation. So only the element which is related to itself, only the elements related to itself must be present in that relation. Next, what about reflexive relation? Reflexive relation for every element in the given set. So here for every element given in the set, for every A belongs to A must be belongs to R. So that means no element can be left over. In the given set. Suppose this A is given as 1, 2, 3. One, 2, 3. Now relation is defined as, that is for every A 1, must be present, 2, 2 must be present, 3, 3 must be present. So this is, so for every a belongs to a, that means no element must be left over. So this is important here. For every a belongs to a, so all elements must be taken into consideration, and that must be related to itself only. So here also 1 comma 1, 2 comma 2, 3 comma 3 is reflexive relation. Then what is the difference between identity relation and reflexive relation? Both are looking same only. Now for that, the difference between identity relation and reflexive relation are, in the identity relation only the elements A must be related to A and no other ordered pair must be present here. So in this 1 1 2 2 3 3, that's all only, no other elements can be present here in the identity relation. Whereas in the reflexive relation, so the relation 1 1 2 2 3 3 1 3 1 4, and so 1 4 is not there, we can take it as 1 2. So here now see the difference. In this relation you should have the minimum, these numbers minimum you must have these elements, then this relation is called as reflexive relation. Apart from this you can have extra elements also in the reflexive relation, whereas in the identity relation only these elements must be there, whereas in the reflexive you must have minimum these three, or minimum these ordered pairs must be present. So from this we can conclude that all identity relations are reflexive relations, but all reflexive relations are not identity relations. So once again repeat, all identity relations are reflexive relations, but all reflexive relations need not be identity relations. So I hope it's clear. Next, symmetric relation. So what is symmetric relation? Symmetric relation, if a comma b is present in the relation, if a comma b is present in the relation, then b comma a also must present in that relation, then such relation is called as symmetric relation. So see, if x comma y belongs to R, then compulsorily y comma x belongs to R, then the relation is called as symmetric relation, otherwise it is not a symmetric relation. We can write this in another form also. X comma y belongs to R, x comma y belongs to R, we can write it as x related to y also. Y comma x belongs to R, so we can write as, that is, x comma y x comma y belongs to R, we can write as x related to y, or y comma x belongs to R can be written as y related to x also. Now see what symmetric relation says. If x is related to y, then compulsorily y also must be related to x. Then we say that relation is a symmetric relation. For example, R is equal to 1 1 1 2 1 3 2 1. Is there? Is it symmetric or not? 1 comma 1, 1 comma 1 is present. 1 comma 2 means compulsorily 2 comma 1 must be present. X comma related to y means y also must be related to x. So 1 comma 2 is there, 2 comma 1 also present. 1 comma 3 is there, but 3 comma 1 is not there. If at all a comma b or x comma y is present, compulsorily y comma x also must be present. Here 1 comma 2 is present, so 2 comma 1 is also present. 1 comma 3 is present, but 3 comma 1 is not present. Therefore it is not symmetric. I hope it is clear. Next, transitive relation. So transitive relation means if x is related to y, if x is related to y and y is related to z, both must be present. Here compulsorily x must be related to y also must be related to z, then only we have to see that x is related to z or not. If these two conditions are not there, it is not necessary that we have to see x is related to. Now once again I repeat this. Whenever x is related to y is related to z, then only we have to check for whether x is related to z or not. If they are not present, then we need not to check this one. Next, when it is not present, we can consider the given relation is, because suppose only one condition x is related to y is there and y is related to z is not there, then it is not necessary to check this. So by triviality, what we can take it as, this relation is transitive relation. So that means any relation which consists single ordered pairs, considered as transitive relations. Now let me see about null relation and universal relation. What about this? Reflexive, symmetric, transitive. Null relation, because in null relation no element will be there, so null relation is not reflexive relation. Null relation is not, or empty relation is not reflexive. Next, symmetric relation. What is symmetric? If a comma b belongs to R and there is no element here, so if a comma b belongs to R, then only we have to see that b comma a belongs to R. Now in null relation no ordered pair is present, therefore by triviality, so null relation is symmetric relation. Transitive relation. What is transitive relation? Transitive relation, if a comma b belongs to R and b comma c belongs to R, then only we have to see that a comma c belongs to R. But in null relation no element is present, therefore by triviality null relation is considered as transitive relation. Next, come to the universal relation. Universal relation. In universal relation, it consists all the ordered pairs, so therefore it is reflexive, symmetric and transitive. Why? Because universal relation is nothing but complete Cartesian product we are considering. Is it clear? Next, come to equivalence relation. What do you mean by equivalence relation? Any relation which is reflexive, symmetric and transitive. So once again, any relation which is reflexive, symmetric and transitive, then such relations are called as equivalence relation. Next, equivalence class. What do you mean by equivalence class? In another way, what I say is, equivalence class is nothing but subset of the given set, provided the relation is an equivalence relation. It is easy to understand. Equivalence class is not a relation. Equivalence class is a subset. Equivalence class is this is just subset of the given set, whatever it may be, subset of the given set, provided the relation defined on that set is an equivalence relation. Now see, an equivalence relation or in an arbitrary set X, then if R is an equivalence relation, then R divides X into mutually disjoint subsets, namely AI, called partitions or subdivisions of X, satisfying the property. What are the properties? All the elements of that subset must be related to each other. No element of one subset is related to any element of the another subset. Then when you do the union of those two subsets, it must be equals to the given set, and intersection of these two subsets must be always null set. Is not zero, must be null set. Then these subsets AI, AJ are called equivalence classes. Let me see one example. A is equal to 1, 2, 3, 4. R is the relation ordered pairs A comma B such that A minus B is even. Now when you consider A minus B is even, so R will be having the ordered pairs 1 1, because A minus B means 1 minus 1 0 is even, 1 1, 2 2, 3 3, 4 4. Next when you come to 1 1 is over. Next 1 2, 1 minus 2 is 1 is not an even, so 1 comma 3. Next 1 comma 4, so 1 comma 4, 1 comma 3. Next we write it as 3 comma 1. Next 1 comma 4, 1 minus 4 is 3, it is not even, so you cannot take it. Then 2, so 2 means 2 1 or 2 minus 1 or 2 minus 3 odd, so 2 comma 4. Then 2 comma 4 means 4 comma 2. So this is the relation. Now whether it is equivalence relation, let me see it first. Reflexive relation. Each and every element for every a comma a belongs to R. Therefore, so 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4 are present. Therefore, it is reflexive. What about symmetric? 1 comma 3, 3 comma 1 is present. 2 comma 4, 4 comma 2 is present. Therefore, it is symmetric. What about transitive? 1 3, 3 1. So 1 comma 1 is present. 2 4 4 2, 2 comma 2 is present. Then 3 1 1 3, 3 3 is present. So it is transitive also. Therefore, the given relation R is an equivalence relation. Now when it is an equivalence relation, the equivalence relation divides the given set into partitions. How it should be? So when you suppose when you take A1 is equal to 1 comma 3, A2 is equal to 2 comma 4. When you divide this, no element must be related to other one. How it is? How to check it? See, first condition: all elements of AI are related to each other. How you consider this? 1 minus 3 is 2 is even. 2 minus 4 or 4 minus 2 is also even. That means all the elements are related to each other. This is the first condition. Second one, no element is related to any element. So that means if you consider one element here and consider another element here, so because relation is mod a minus b, that means 1 minus 2. So 1 minus 2 is 1, which is an odd number. So therefore this element cannot be related to this one. The third condition is union of this must be equal to the given set. That is, when you make union of these two subsets, 1, 2, 3, 4 is nothing but the given set. When you take the intersection of these two sets, you have to get null set. So when you take these two subsets, is nothing but null set. Therefore R is a equivalence relation dividing the given set into partitions. These partitions are called, or subsets are called as equivalence classes. This is just for understanding. But how do you write notation wise? Now you see, notation wise we write it as equivalence class A. Or write it as equivalence class A. That is nothing but set of all x such that x belongs to the given set. Set of all x such that x, that means set of all elements in A such that condition A must be related to Ex. Suppose in the previous example, if you take equivalence class 1, so how do you write this? Instead of writing that subset, how to make into subsets? It is a big doubtful question for everybody. So for that, this is very much helpful. So equivalence class 1 is equals to, how do you write as per the definition? Set of all x such that x belongs to A, comma, A means 1 must be related to Ex. What is the meaning of 1 related to Ex? The meaning of this is modulus of 1 minus x is even. Now you can substitute x values 1, 2, 3, 4 from the given set. Suppose when x is equals to 1, when x is equals to 1, 1 minus 1, 0 is even. So it is satisfying. When x is equal to 2, when x is equals to 1 minus 2 is an odd number, so not satisfying, you cannot write it. Next, 3. When you take x is equals to 3, 1 minus 3 is even, therefore 3 I can write it. Next, 4. 1 minus 4 is odd number, it is not an even, so I cannot. So equivalence class 1 is nothing but 1, 3. Suppose I need equivalence class 2. Equivalence class 2. So same definition. Set of all ordered pairs, set of all x such that x belongs to A, and this 2 must be related to x. What do you mean by this? 2 related to x means it is modulus of 2 minus x is even. So now you have to substitute x values from the given set 1, 2, 3, 4, because A is equal to 1, 2, 3, 4. Substitute. When A is equal to 1, so it is an odd number, so you cannot. But when x is equal to 2, 2 minus 2, so this is 2. When x is equal to 3, so it is odd number. When x is equal to 4, it is even. Therefore, equivalence class 2 is nothing but set of 2, 4. So I hope it's clear about the equivalence class. Now let we come to the problems. First one. Determine whether each of the following relations are reflexive, symmetric and transitive. First relation is, it is defined on set A, means R is subset of A cross A. So that means in each and every ordered pair, the first and second elements compulsorily they must belongs to the given set only. Now the relation is defined as x comma y such that 3x minus y is equal to 0. Now let me see this. The relation is given as 3x minus y is equal to 0. That implies y is equal to 3x. So relation is, when x is equal to 1, y is equal to 3. When x is equal to 2, y is equal to 6. When x is equal to 3, y is 9. When x is equal to 4, y is 12. When x is equal to 5, y is equals to 15, but 15 is not present. So this is only the relation. Now let me check reflexive. What is reflexive property? For every A belongs to A, or for every A belongs to A comma A must belongs to the relation. That means, so one is A is having the elements, A is having the elements 1, 2, 3 up to 14. That means the relation must have the ordered pairs 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4 up to 14 comma 14. But here nothing is there, therefore it is not reflexive. What about symmetric? If A comma B belongs to R, compulsorily B comma C also belongs. If A comma B belongs to R, then B comma A also compulsorily must belongs to R. So what is symmetric property? If A comma B belongs to R, implies B comma A also belongs to R. But whereas here 1 comma 3 belongs to R, but 3 comma 1 does not belongs to R, therefore it is not symmetric also. What about transitivity? Transitivity is if A comma B belongs to R and B comma C belongs to R, then A comma C belongs to R. So here one comma 3 belongs to R, 3 comma 9 belongs to R. So whenever these two are present, that means A comma B, B comma C present, then only we have to see whether A comma C belongs to R. So in this case 1 comma 3 belongs to R, 3 comma 9 belongs to R, but 1 comma 9, that is 1 comma 3 belongs to R, 3 comma 9 belongs to R, but 1 comma 9 does not belongs to R. Therefore it is not transitive. So for the first case, the given relation is neither reflexive nor symmetric nor transitive. Now come to the second case. Second one is R is defined on set of all natural numbers and defined as y is equal to x plus y and x is less than 4. So R is x such that y is equal to x plus 5 and x is less than 4. So that means when x is 1, y is 6. When x is 2, y is 7. When x is 3, y is 8. Now come to reflexive. Now you have to answer. Reflexive property. Reflexive means each element must be related to itself. That means 1, 1, 2, 2, 3, 3 and so on. Here nothing is present, therefore it is not reflexive. What about symmetric? In symmetric, 1, 6 is there, but 6, 1 is not present, therefore it is not symmetric. Transitive. What do you mean by transitive? If A, B belongs to R and B, C belongs to R, then only you have to check. 1, 6 is there, but 6, that connection is not there. So you need not to check. 2, 7 is there, 7, is not there. 3, 8 is there, that link is A, B, then compulsorily B, C must be there. Then only transitivity you have to check it. 3, 8, 8, that connectivity is not there. Therefore, by triviality, this is transitive property. Next, come to third question. Third question. A is 1, 2, 3, 4, 5, 6. Then relation is given as y is divisible by x. Y is divisible by x, or we can write it as x divides y. Y is divisible by x or x divides y. So what is the relation? X divides y. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. 2 cannot divide 1, so 2, 2 cannot divide 3, 2, 4, 2, 6. Then 3 cannot divide 1, 2, so 3, 3, 3, 6. Then 4, 4, 5, 5, 6, 6. Now let me check about reflexive. Set is consisting 1, 2, 3, 4, 5, 6, and we have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Therefore, it is reflexive. What about symmetric? Now let me see. 1, 2, 1, 2, 2, 1 is not present. Therefore, it is not symmetric. Transitivity. Transitivity means A, B also must belongs to R and B, C also must belongs to R. Then only we have to check for A, C belongs to R or not. Now let me see. 1, so when you see 1, 1, 1, 2, 1, 2, so all are present. When you come to 2, so when you come to 2, 2, 2, 2, 6, so all are present. 3, 3, 3, 6, 3, 6 is present. So all elements, all conditions will be satisfying. Therefore, it is transitive. Next, come to fourth one. Relation R in the set Z of all integers defined as R is equals to set of all ordered base x comma y such that x minus y is an integer. Set of all ordered base x comma y such that x minus y is an integer. Now when you take a reflexive, because this is a bigger set integers, we cannot, like previous problems, we cannot write specifically relation, so we have to speak in general. So how do you write? For every x belongs to integers, x comma x belongs to R implies x minus y, that means here x minus x is equal to 0 is an integer, So once again I repeat, now fourth problem we have to do in general. So how to do this? For every x belongs to, because all given as in integers, for every x belongs to z, reflexive property is what every element must be related to itself. X comma x belongs to R. What is the meaning of that? The meaning of this one is x comma x belongs to R, meaning is nothing but x minus y is an integer. Now replace y by x, that is x minus x is equal to 0, which is an integer. Therefore R is reflexive. Next, what about symmetric? Symmetric is what? If x comma y belongs to R, then only y comma x also belongs to R. Now let me see. Let x comma y belongs to R. What is the meaning of this? X minus y is an integer. When x minus y is an integer, y minus x is also an integer only. That means y comma x also belongs to R. So once again I repeat, what is the symmetric property? If x comma y belongs to R, the condition is if x comma y belongs to R, then only y comma x also belongs to R. We have to see it. Now, so let me suppose that x comma y belongs to R. But as per the relation, x comma y belongs to R means what? X minus y is an integer. That is the relation. So x minus y is an integer, which implies y minus x is also an integer only. That y minus x is an integer means what? Y comma x belongs to R. When x comma y belongs to R, y comma x also belongs to R for all x comma y belongs to z. Therefore, the relation is symmetric. Next, we come to transitive relation. What is transitive relation? If x comma y belongs to R and y comma z belongs to R, then x comma z also must be belongs to R. Now let me suppose that x comma y belongs to R and y comma z belongs to R. Let x comma y belongs to R. What do you mean by this? According to relation, x minus y is an integer and y comma z belongs to R. What do you mean by this? Y minus z is also an integer. Now these are true. X minus y is an integer, y minus z is also an integer. Then what about x comma z? When x minus y is an integer, so we have to check whether xz belongs to R or not. So xz means what? X minus z. We can write x minus z as x minus y minus of y minus z. So x minus y is an integer minus minus y plus x minus y plus y minus z. X minus y is an integer, y minus z is also an integer. So integer plus integer is nothing but an integer. So therefore when x comma y belongs to R, y comma z belongs to R, x comma z also belongs to R only. Therefore the relation is reflexive, symmetric and transitive. Therefore it is an equivalence relation. Next, come to the last case of this question. X and y work at the same place. So reflexive. X comma x. X comma x. That means x and x work at the same place. Therefore it is reflexive. Symmetric. X comma y means x and y work at the same place. So y and x also work at the same place. That means y comma x also belongs to R. Therefore it is symmetric also. Next, x comma y means x comma y belongs to R means x and y work at the same place. Y comma z belongs to R means y and z work at the same place. Then x and y are working at the same place, y and z are working at the same place means x and z are also working at the same place. Therefore x comma z also belongs to R. Therefore R is reflexive, symmetric and transitive. Therefore it is an equivalence relation. So rest second, that is B, C, D, E. Just you try at home. Thank you.